Hey, what's up everyone? Welcome to Thermodynamics Part 4. Today we're going to go over spontaneity and Gibbs free energy. So I want to start off with spontaneity and to demonstrate what that is, I want you to look at the rusting of iron. And the thing about the rusting of iron is that if you leave any piece of iron out on the outside, it's going to rust. And that is exactly what a spontaneous reaction is. These are going to be processes that favor the formation of products under certain conditions. And so there are certain reactions that occur with no outside input. A lot of the times, if you just allow a system to be, a certain reaction is going to occur. And sometimes some reactions are not going to occur. We call those non-spontaneous reactions. A really cool reaction that is technically spontaneous is diamond going into graphite. Technically, this reaction is spontaneous. If you give it enough time, a diamond will turn into graphite. But this kind of brings up a big distinction in thermodynamics, in that thermodynamics tells us nothing about the rate of a reaction. In fact, for a diamond to turn into graphite, that would take billions of years. So when we're studying thermodynamics, we can use thermodynamics to tell us whether or not a reaction is going to occur, but we cannot use that. We use thermodynamics to tell us how fast a reaction is going to occur. For that, you're going to need kinetics, which I believe is the next unit. Okay, now that we have an idea of what spontaneity is, I want to talk about Gibbs free energy. So Gibbs free energy is defined by this equation, where the change in Gibbs free energy is equal to the change in the enthalpy minus the temperature times the change in entropy. And so in order to practice using this equation, I have a little practice problem. What is the standard Gibbs free energy formation of NH3 at 298 Kelvin? So the reaction for the free energy the formation equation for this would be NH3 obviously at the product side, but it would also be H2 and then N2. And so you would obviously need only 1/2 of N2 and you would need 3/2 of H2. And so now you need to figure out the enthalpy and also the entropy, the change in them. And so you can just do that by doing their formulas, which is the sum of the enthalpies or entropies of the products minus the sum of the enthalpies of the entropies of the reactants. So let's do that for all of them. Products for NH3, let's start with the entropy first, or enthalpy, sorry, minus 46, and that's going to be minus 1/2 times 0 plus 1/2 or 3/2, sorry, times 0. And so our change in enthalpy is going to be minus 46 kilojoules per mole, and our entropy is going to be 193, and it's going to be minus 1/2 times 192 plus 3 over 2 times 131. So our change in entropy comes out to about negative 0.0995 kilojoules per mole times Kelvin. So if we're trying to find the standard Gibbs free energy of formation, we would take the enthalpy, and we know that the enthalpy is minus 46 minus the temperature temperature is 298 times the change in entropy 0.0995, and once we do the calculation for that, that is going to be 298 times negative 0.0995. That's going to be about negative 16 kilojoules per mole. And that is answer choice B, and that is the correct answer. So I guess this just kind of ties in everything we've learned about these calculations. And I guess these calculations are kind of annoying, and they're really trivial to explain. So they might seem a lot harder than they really are. But I promise you, once you go and you do some examples, you'll realize that these aren't crazy hard to do. Also, it's important to make sure that the units for the enthalpy and the units for the entropy are the same. So for over here, you were given in joules, but over here you were given in kilojoules. So make sure you convert either kilojoules to joules or joules to kilojoules based on whatever answer choice you have. So why is Gibbs free energy important? Well, Gibbs free energy is going to tell you whether or not a reaction is going to be spontaneous or not. So if your Gibbs free energy is 0, then that means your system is at equilibrium. If your Gibbs free energy is, or your change in Gibbs free energy is greater than 0, then that means your reaction is non-spontaneous. But if your change in Gibbs free energy is less than 0, then that means your reaction is spontaneous. So if we were to make a chart with values of enthalpy and values of entropy, what would these values of change in Gibbs free energy be? If we had a negative value for enthalpy and a negative value for entropy, what would Gibbs free energy be? Well, they're not. Well, these like calculations aren't very hard to do, but they are kind of annoying and they take a bit of time. So a lot of good people on the internet have put the answers out. If you have a negative enthalpy and a positive entropy, your reaction is going to be spontaneous at all temperatures. If you have a positive enthalpy and a negative entropy, that's going to be non-spontaneous at all temperatures. Negative enthalpy, negative entropy, spontaneous at low temperatures. Positive enthalpy, positive entropy, spontaneous at high temperatures. I just like to think of like these last two. Negative is like low, so spontaneous at low temperatures, and then positive is high, so spontaneous at high temperatures. Maybe that helps you think about it. So let's do a bit of practice with what we just learned. For an endothermic reaction to be spontaneous under standard conditions at constant pressure at some temperature T, which must be true? Okay, so we know our equation is going to be something like this, right? Times T. I think I'm like switched up the order of the delta S and the T. And in order for that reaction to be spontaneous, that needs to be less than 0. Now, using this, we can do some algebraic manipulation. So we can first take the delta T, delta H to the right-hand side. So that would be minus delta H. And we can divide this whole thing by negative T. But if you remember from algebra class, once you divide an inequality by a negative number, you need to flip the sign. So really, it's going to be delta H over T. So that by default takes out C and D. And in order to find out which one of them is accurate for A or B, we have to look at whether or not it's going to be greater than or less than. We know that the delta S is going to have to be greater than that value, and so that answer would be A. Answer choice A, and that is in fact the right answer. Okay, let's move on to the progression of a reaction in terms of Gibbs free energy. So in like normal reactions that we've dealt with so far, even depending on whether or not your delta G is positive or negative, you're going to go from a state of pure reactants where the free energy is going to be high. You're going to start off at a state where you have a lot of free energy, and in every reaction, the reaction ends when you have reached the lowest free energy. And so some of the times it's going to be this linear line where it just goes down from pure reactants to pure products. And sometimes it goes up that way. The reason positive delta G means non-spontaneous is because there would be an increase in free energy. And a reaction does not want to increase its energy, it always wants to decrease its energy. And we can use that that one piece of thermodynamics to explain why equilibrium reactions occur. For equilibrium reactions, they're not going to be this linear line. In fact, if we look at the progression of a reaction from pure reactants to pure products, it goes from here to here. But in fact, at pure products, that is not where the system is at the lowest free energy. At the lowest free energy is like somewhere in the middle, right here. At this point is where the reaction will stop. At this point is where you reach equilibrium. So we are talking about equilibrium reactions. All reactions end when they have reached their lowest free energy. And sometimes you're going to end that reaction where you're going to have more products than reactants like you do on this side. But sometimes you might end it where you have more reactants than products. So you're going to end your reaction over here because that is the lowest point of the entire reaction in terms of free energy. And so for more examples, again, lowest energy is here. So whenever that reaction goes and progresses onto here, it's going to stop. It's not going to go all the way up here. It's not going to do that because you would need to increase free energy, and reactions don't do that on their own. So in this case, you're going to have more products than reactants. But on this side, you realize that the lowest point is about here. And that's kind of more reactants than products. If we say this is halfway, where the reactants is going to be equal to the products, then you're going to see that you're going to have more reactants than products on this side, but you're going to have more products than reactants on the left-hand side. And so we actually have we use a value to determine whether or not there's going to be more reactants or products, whether or not a reactant or product is going to be favored in an equilibrium reaction. We describe that as the equilibrium constant. So if the equilibrium constant, or K, is less than 1, equilibrium is going to favor the reactants. But if equilibrium is greater than 1, equilibrium is going to favor the products. So for this thing on the left here, equilibrium, or the equilibrium constant, is going to be greater than 1 because the equilibrium is favoring the product, sorry. And for this one, K is going to be less than 1 since the equilibrium, it favors the reactants. Now, as it turns out, you can relate the equilibrium constant to free energy using this equation right here, where delta G is equal to the negative R times T times the natural log of K. And so in order to see how that's used, let's look at this example right here. The KSP of barium sulfate at 298 Kelvin is 1.1 times 10 to the negative 10th. What is the delta G at 298 Kelvin for the following reaction? And now this question actually has a couple tricks. This K value that you're given right here is actually not the one you're supposed to use. And we'll figure out, like once we get to equilibrium, you'll realize why that is. But our only goal here is just to figure out how to use this equation. So I'm going to tell you that the real K value that you use is going to be this value right here. And this isn't some random value I pulled out of nowhere. You can actually get this value if you if you knew equilibrium and like you knew how to manipulate this K value to get the K value that you really need. So we can use this K value to find out our delta G. So our delta G is going to equal minus 8.3145 times the temperature in Kelvin, so 298. And then the natural log of our K, which is 9.09 times 10 to the 9th. And so if you just plug all these numbers into a calculator, negative 8.3145 times 298 times the natural log of 9.09 times 10 to the 9th, you are going to get about negative 57 kilojoules per mole. And that is answer choice A. And we are correct. So again, don't worry about where we got the K value from. You'll learn how to do that in equilibrium. Just know that this equation exists, and sometimes questions do come up on the test concerning this equation. That's all I have for this lesson. I hope you learned something about Gibbs free energy and spontaneity. I hope you'll join me for the next lesson. Next lesson, I think, is the review lesson, but I'm not entirely sure. Anyways, I hope to see you there, and thank you for watching this video.